Ladies and gentlemen, my name is Michael Hennerich. I work for Analog Devices in the System Development Group. I'm also a licensed ham amateur for almost 30 years now, so it's kind of proud to stand here and talk to this well-educated crowd here. Today I want to focus on a multi-channel phase coherent transceiver system with a GNU Radio interface. So yesterday there were some good talks. We learned about LO synchronization and baseband synchronization and how important those things are in the multi-channel systems. Today I want to focus a little bit on, oh, we're not seeing the presentation. Why?
I tried screen presenting. Your second display wasn't.
Duplicate slideshow. Here we go. Today I want to focus a little bit on how it's being practically implemented on a system. I have lots of slides, so in the interest of time, I want to skip some of them. But I wanted to start with where our multi-channel phase coherent systems are important. And the first thing that came to my mind is basically a radar system. There are kind of different radars, but phased array techniques are pretty common. So a traditional FMCW radio system requires a lot of bandwidth, which is typically not that much applicable to integrated RF transceivers, but next-gen MIMO or phased MIMO systems are very well suited for integrated transceivers. So what are the important system factors? It's low phase noise, high bandwidth, and of course synchronization between channels. Also, dynamic range is very important. So I mentioned phased array. I want to give a brief introduction what phased array is. So radar systems utilize an array of elements. There's either analog or digital phase shifters, which provide directionality. This eliminates mechanical rotations of the antenna. And typically, each of these channels in this multi-channel system processes a different phase. So you can steer the wavefront out of the antenna at a certain angle. So there are two main beamforming techniques. One is analog beamforming, where the phase shifting happens in the analog domain and typically uses discrete phase shifters. The other one, which is becoming more and more popular, is digital beamforming, where the beamforming happens in the digital domain by using numerical controlled oscillators or digital filters. The main improvement or the main advantage is the multi-beam capability of such a system. So you can steer out multiple beams at the same time, and you can steer them really, really fast. There are also some mixtures between analog and digital beamforming, which is called like hybrid beamforming, where you basically use both techniques at the same time. Here's an example of an analog beamformer. This is a 4-channel one. It can adjust the phase between 0 and 360 degrees with some certain resolution, and you can also store some settings in a very fast hopping memory, and you can recall it very, very fast. So there are phased array dynamic range and spurious improvements that can happen. So after RX phase and amplitude calibrations, the system is time and amplitude aligned, and the system performance is better than an individual receiver. So when the number of channels are being doubled, the effective number of bits are also doubled, and the noise spectral density is lowered. And also, if the channel spurious contribution are uncorrelated, the spurious do not add, but the noise floor lowers. So we can see a 10 log n improvement in dynamic range. Similar things apply for the TX as well. So if the TX amplitude is phase calibrated, the TX signals can be combined constructively. Spurious system phase noise improvements can be achieved. But those improvements rely on uncorrelated channels, which typically require separate PLL sources to the subarrays, so the noise do not add up constructively. So if they are uncorrelated, we can also see a 10 log n phase noise improvement, which leads that the channel throughput can be increased. So how to make those channels being uncorrelated? There's an interesting application note. It's called RF Transceivers enable for spurious decorrelation in digital beamforming phased array. And the main idea behind this is in each of your channels, you offset your local oscillator by a certain offset, and then you correct for that offset in the digital domain using a numerical controlled oscillator. And to the right, you see if they are not correlated, not decorrelated, they basically add up the spurs and the images, and if they are uncorrelated, they don't add. So what I mentioned integrated transceivers. What are those? It's basically a single chip which contains a full RX and a full TX path with ADCs, stacks, down converters, mixers, filters, gain, amplifiers, and so forth. There's often a microcontroller on chip which does a lot of additional calibrations. So how does integration lead to a smaller footprint? So these integrated transceivers can enable lower size, weight, and power SDR systems by having multiple channels on the same chip, and that leads to that they can be used as a backbone in phased array systems. So I mentioned the built-in calibrations. So just to mention a few, there's a digital pre-distortion available on some chips. There's also some spurious rejection algorithms, and of course there's quadrature correction, LO leakage correction, and a few other things. So the ADRV9009 has been mentioned over the last 2 days quite a few times. This is how it looks like. It's a 2RX, 2TX system. It features 200 megahertz bandwidth and has a lot of additional digital features built into the chip. The multi-channel system that I'm talking about today is basically built on the RF SOM. It's basically 2 of those chips, making it a 4x4 on a PCB together with the ginormous MPSoC FPGA from Xilinx. There's, in addition, multiple banks of DDR4 memory and also complete integrated power. So, but the main topic is about talking about synchronization and how we can phase align multiple of those modules in a system that can scale. So there are multiple things that needs to be calibrated, and they are typically done in a certain order. So for example, there's the clock synchronization, where they basically synchronize the clocks across multiple layers in your topology. Then there is the multi-chip synchronization, where you align the basebands of all these different chips. Of course, there is a digital link between the FPGA and the transceivers. Typically, this is a JESD204 interface that also needs to be aligned, calibrated, so that you have a deterministic latency. And of course, yesterday we heard about LO synchronization, and that's what I call here RF phase synchronization, which is also important. And of course, there's more on the application layer that we are not going to talk about here today. So let's start looking into JESD204 and what it is and how it can be synchronized. So first of all, traditionally LVDS, parallel interfaces have been used between converters and FPGAs. As the number of channels increase, this becomes not practical anymore, and also if the data rates increase, you're kind of limited by the electrical signaling. So newer converters use a high-speed serial interface using the JESD204 standard. So what is the JESD204 standard? It's designed as a high-speed serial link, data link between converter devices and a logic device. It supports up to 32 lanes per link, and the lane rate or the link rate can be up to 32 gigabits per second with the latest addition to the standard in 204C. The standard also describes the data mapping and framing, the multi-chip synchronization, and also how deterministic latency can be achieved. If you look at the architecture of such a system, there's typically a transmitter, a receiver, and then there's a clock chip. Between the transmitter and the receiver, there are the high-speed lanes, the link. Then there is another kind of a handshaking synchronization signal that goes from the receiver to the transmitter. And for subclass 1 deterministic latency, there's also a SysRef signal required, which synchronizes both transmitter and receiver to the same instant in time. So there are multiple layers. There's a physical layer, which describes the high-speed SerDes, the clock recovery, and the signal shaping. A link layer, which has like the character replacement, the 8B10B coding, a transport layer that I'm not going to talk about today, and then, of course, there's an application layer. So to understand deterministic latency, also only the link layers is interesting here. I need to skip a little bit, otherwise this is all obvious. What is an FPGA? What is a logic device? And what is a link? I mentioned it. The link consists of multiple independent lanes. It uses 8B10B encoding and typically has an embedded clock, or it has an embedded clock. It also supports data scrambling. So how does link synchronization work in general? So the receiver asserts the synchronization pulse or the synchronization strobe. Then the transmitter repeatedly sends the K character. The receiver performs what's called being a code group synchronization and character alignment. After that's being done, the receiver deasserts the sync, and the transmitter sends the initial lane alignment sequence followed by the data. So latency. Propagation over the data link takes time. JESD defines the latency as the time difference between when the sample is inserted in the TX framer and outputted by the RX framer. So part of this latency is being fixed. It's digital pipeline delays, trace lengths, and also part of this latency depends on manufacturing and environmental conditions such as process, voltage, temperature, and also like PCB propagation delays. A lot of systems are latency sensitive, so all closed loop control systems, and of course also radar is one of those systems. So what is deterministic latency? So latency can be defined as deterministic when the time from the input of the JESD204 transmitter to the output of the receiver is consistently the same number of clock cycles. So in parallel implementation, this is rather simple because the clocks are carried in parallel with the data. In serial implementation, this is a bit more difficult because there are multiple clock domains. The standard says that end-to-end latency is consistent and deterministic across PVT and also between power cycles, link up, link down, and so forth. All the non-deterministic components are not removed, but however, they are compensated, and that basically is something that I want to talk a little about in the next slides. There are different subclasses. Subclass 0, there is no deterministic latency. In subclass 1, it's using SysRef to achieve that. And what basically SysRef does, it aligns the local multi-frame clock. It's a clock that's running in the link layer of the JESD stack. And this SysRef pulse is basically synchronizing this clock across multiple devices. So I mentioned it before, SysRef is the pulse that does it, and SysRef is source synchronous to the device clock. So deterministic latency is achieved by using an elastic buffer with an appropriate release point. So we see the lanes here in this example, lane 0, lane 1, and lane 2. They all arrive at a different time. And we need to make sure that the release opportunity on the link happens after the last lane arrives. And the release opportunity is synchronous to the LMFC. Okay. So a lot of people think JESD204 is complicated, and in theory, it is a little bit complicated, but We have created this JESD interface framework, which makes it much, much simpler. It's basically an integrated software and hardware framework that covers the entire stack. So we have hardware, we have generated HDL blocks for the link layer. We have software drivers that configure the link layer, the physical layers, as well as the transport layers. It has been co-designed for improved interoperability, so it is really a framework. And the key features here are that you basically say, I'm a converter, I have this amount of converters, it's like link parameter equals M. I want to use that many lanes, and I want to run at that baseband rate, and then everything is being set up and configured without any other user intervention. So we also try to make it kind of fail-safe, and because a lot of things can go wrong, we have implemented statistical eye scan, so you can look at the eye opening of your gigabit serial links without using expensive instrumentation devices. It's actually a feature that's being built into the Xilinx gigabit transceivers that's being used here. We have clock rate monitoring, so we can detect bad clocks, lane sequence monitoring, which one arrive first. You can see during the ILA phase, there's also some data transmitted over the links, so you can see if you have a lane swap, which is rather, because the lanes can be swapped multiple times in hardware, in software, inside the converters, inside the FPGA, so sometimes this can cause problems. We also have SysRef alignment monitoring, which basically helps you to detect setup and hold violations for the SysRef signals. So the next thing in the synchronization is the multi-chip synchronization. This is where we synchronize the baseband signals or the baseband path of multiple transceivers. It's also using the SysRef and the ref clock, but this time it's not synchronizing the JESD link, it's more synchronizing the internal dividers of the chip. The NCOs, all the state that's in the chip needs to be synchronized if you want to synchronize multiple parallel instances in your multi-channel system. So where are those latencies in a modern transceiver? So of course there's analog circuitry delay, there's ADC cycle delay, and of course there's digital processing pipeline delay in all the digital filters, in the numerical controlled oscillators, in the quadrature error correction things. And if you don't reset them, you end up with non-deterministic behavior of your system. So the latency is fixed, is deterministic, but it depends on settings just like what's the baseband rate, what's the ADC clock, and of course, what of those digital filters are being enabled, and how many coefficients are in my FIR filter, and if this correction algorithm is enabled or not. So what is RF phase synchronization? Yesterday it was referred as LO synchronization. The RF phase synchronization is a new feature on our latest generation of RF transceivers. It provides a deterministic phase across power cycles, LO frequency changes between initializations, as well as across temperature. It works across multiple devices in a multi-channel system. What we need to say here is that the phase is not zero between all them, but it is fixed, and it's consistently fixed. So each of those transceivers do have a fixed phase. So how can that be measured? Here we see some phase values of different transceivers, and after this phase calibrations, they all settle to the same value back. can also be shown with multiple devices. They all settle to the same value after the phase synchronization. And also here, this is a phase analyzer. We see that the phase goes all over the place during initializations or during PLL frequency changes, or if you turn the radio on and off. But afterwards, it settles back to the original value. Also, for factory calibration, you can actually take this phase offset of your given transceiver and store it, for example, in an on-chip memory. The overall system considerations, so the overall phase synchronization is determined by a number of factors. First of all, the board level clock routing, the on-chip reference path routing, the PLL and LO divider paths, and of course also the RF and antenna paths. The LO phase synchronization that I'm talking here about method addresses only the initial PLL phase and LO divider stage. So if you wouldn't do that, every time you change a frequency or do a hop, your phase would be all over the place because the internal dividers are not being reset or are not being tracked. Also, there's a temperature dependence and a drift, and also this is being addressed by this RF phase synchronization feature. So what does it bring us? It gets us a more consistent startup condition, and your antenna calibration needs to be run less frequently. You would need to run you always have like a lot of phase difference just by your antenna path. So think about you have a 300, let's take an easy number, 3 gigahertz divided by the speed of light. It's 100 millimeter wavelengths. For example, if your cabling or your antenna elements just drift by 1 millimeter, that gives you a phase offset by 3.6 degrees. So just temperature changes a lot of phase, so you always need antenna calibration, but you don't need to run that frequently. So the last point here is the distributed multi-chip clock synchronization. So what are the requirements? The requirements are that all clocks need to be aligned across multiple layers in your clocking tree. You also need to meet setup and hold for synchronization signals, just as sysref. The problems are if you increase the number of channels, also the number of clocks increase in your system. In a multiple device clock structure that is based on simple clock buffers, controlling setup and hold is really sometimes challenging. And of course, very important is also that you maintain a deterministic phase across multiple layers in your clock hierarchy, while maintaining very important things like clock jitter, phase noise, and you don't want to add additional clock spurs to your downstream devices. So in general, there are two different techniques on clock distribution. One is really what's being called clock distribution. That means you distribute the maximum clock that's required to all the downstream devices, and all the downstream clock distribution chips are just using a down-divided version of that clock. So you only need one VCO in the system, and all the noise is kind of correlated. And the other thing, this becomes really difficult if you have like larger systems or distributed systems. So the other method is what's being called reference distribution. This is where a much lower reference frequency is distributed across multiple layers in your clock topology. But this reference clock is much lower frequency, and you can also route it through backplanes and other things. So the penalties here is that every stage needs another PLL and VCO, which can be rather a little bit more expensive. So there's some cost penalty involved with that. At the beginning, we heard about that correlated phase noise can be sometimes good and can be sometimes bad. When you use the reference distribution, it is actually pretty good. So it gets you this SFDR improvement. What's being used on the RF system on module is an HMC 7044. We can use it in both techniques, clock or reference distribution. It has a lot of things that makes it kind of unique, because we can both reference and clock distribution, and it can be synchronized across multiple layers in the system. It has 14 low noise configurable outputs, and also each of these outputs can be fine delay adjusted. This is how the setup is on a 4R 4T on the SOM itself. So we have two ADRV9009s and one HMC 7044, and it's just like providing ref clock and sysref to both devices. There's nothing special in this setup. But of course, we see the sync input, which allows that multiple of these system on modules can be synced. So this is the example for an 8R80 synchronization, that you always add another layer with another clock chip on top of it. And it's always going like top-down synchronization. And as we can see, we can play this game for a little bit more, and we can expand the clock tree and also scale our number of channels using this approach. So multi-channel phase offset validation. So if you want to validate that your multi-channel system is phase coherent, the best way is to actually measure the phase. There are many ways to measure phase, but I want to discuss two here. One is averaged instantaneous phase, and the other one is using a cross-correlation method. What kind of source signals do we use? We either use sinusoids with the average instantaneous phase method, or we use a noise source with the cross-correlation method. Typically, they both need to be high signal-to-noise. Travis, my colleague, implemented two hierarchical blocks that are both available on our GitHub. I think one of the slides actually have the URL. So this method is easy to implement, works great with sinusoids, but is a little bit more sensitive to sample offset. How it works: we take the channel, multiply conjugate, compute the angle, then we kind of multiply constant to scale it into degrees, and then we average it. The other hierarchical block is the cross-correlation method, and it basically uses forward FFTs, multiply conjugate, do a reverse FFT, then we compute the magnitude spectrum, and then we take the bin with the highest power, and then select the complex value from it, and on that bin, that represents the phase of our signal. Also, the index from that bin can directly translates into a sample delay. This is how the measurement setup looks like. We use the 1TX from one device, either provide us like a sine wave or play back a noise spectrum, feed it into a 4-way power splitter, and then feed the signal back into the receivers. This is how the flow graph looks like for the average instantaneous phase. We have the ADRV9009 GNU Radio source, feed it in the hierarchical block, and visualize it. This is an example here. On the bottom, we see a frequency spectrum, the time spectrum, and the phase. So the blue one is the reference, and the two other channels are the other two receivers. So you can play that over and over. You can restart the system. You will always measure the same phase offsets. This is the flow graph for the cross-correlation method. Again, the source. This time we correlate only like 2 channels. It goes into the phase estimator block. Then we average and also visualize. This shows the cross-correlation, then the sample offset, and so we see we have no sample offset, and we also can measure the phase. You can start playing with your radio. If you start turning on some calibrations on one device and not on the other device, you actually see how that you basically get a sample offset. So these blocks are really handy, and if someone is interested, they exist on our GitHub. So what are the conclusions? End-to-end deterministic latency in RF phase and frequency synchronization can be realized in a multi-channel system using the latest generation of integrated transceivers. The multi-chip LO phase synchronization simplifies phased array beamforming. The spurious force decorrelation can improve your system dynamic range and also your transmit phase noise. It always requires a very flexible clocking and synchronization topology, and of course also all your traces, everything needs to be impedance and length matched in order to actually synchronize those things. The phase offsets can be measured, they can be avoided, or most of the time they're just compensated. And last but not least, GNU Radio is a very effective tool to build, model, analyze, and visualize multi-channel software-defined radio systems. So that kind of finishes my talk today.
Round of applause, round of applause.